Let's draw the Lewis structure of NH3 ammonia. So nitrogen is happy at 5. Hydrogen is happy at 1, but we've got 3 hydrogens, so that's going to be 1 times 3 is 3. So 5 plus 3 is 8. So our goal here is to get 8 valence electrons around the NH3 molecule, also known as ammonia. So we're going to have nitrogen as our central atom, not hydrogen, because you don't know which of the 3 hydrogens you want as central. So we're going to make things easy and make nitrogen your central atom, and then we will have our bonds with our hydrogens. Okay, so 8 valence electrons, right? So 1, 2, 3, 4, 5, 6. I'm going to put the 7 and 8 on the nitrogen. It doesn't make sense to put it on the very small, very basic hydrogen atom. It makes sense to put it on the more complicated nitrogen. Nitrogen can accommodate that. So this would be the structure of NH3 ammonia. Let's look at the formal charge considerations for our central atom ammonia. So formal charge 1, 2, 3, 4, 5. So nitrogen is happy at 5. 5 minus 5 is 0. Let's look at the octet rule for this nitrogen. Octet rule, we count everything individually. 1, 2, 3, 4, 5, 6. So they're shared. 6, 7, 8. So that that nitrogen has a minimized formal charge and satisfies the octet rule. Let's look at the hydrogen here. Let's look at the formal charge for the hydrogen. 1. Hydrogen is happy at 1. 1 minus 1 is 0. So let's look at the octet rule for hydrogen. 1, 2. Okay, so hydrogen is happy with that octet. This is not how the structure is three-dimensionally. So we're going to count the number of bonds and lone pairs. So we have 1 bond, 2 bond, 3 bonds, and a lone pair here. That's really going to mess up the structure, distort the structure. So we have 3 bonds and 1 lone pair. So 3 bonds and 1 lone pair. We're going to use this here, table 10.2 of your book. Because 10.2 of the book is talking about lone pairs. You see, the previous structures we did had no lone pairs on the central atom. Here, if you have lone pairs on the central atom, that's what you are going to look for. And again, we're looking at the geometry of the molecule. So 3 bonds and 1 lone pair. So 3 bonds, number of lone pairs is 1. And this is going to be the number of bonding pairs, 3 bonds. So number of bonding pairs, 3 bonds and 1 lone pair. 3 bonds and 1 lone pair. The electrons are going to orient themselves in a tetrahedral. So this forces the electrons to take a tetrahedral shape. But that's a lone pair, so that's not really. So 3 bonds and 1 lone pair. So we're going to look at the number of bonding pairs, which is 3. Number of lone pairs is 1. The electron pairs we're not going to concern ourselves with, but we are going to concern the fact is that lone pair forces the molecule to adapt a trigonal pyramidal relationship or trigonal pyramidal geometry. So that is what NH3 would look like. So you'd have a hydrogen coming towards you, maybe a hydrogen coming out, maybe a hydrogen on the plane, but that lone pair sort of compresses the molecule. I want to say squishes it, in the sense it's like taking a hammer and hitting it, because that lone pair is not bound to any substituent. It's just by itself. Because it's not bound to any substituent, it sort of bends and distorts the molecule. The bond angle also is not perfect. I do not know the bond angle off the top of my head, but it's not 109.5. It's not a clean number. It's like 107.6 or some messy decimal. So to try to draw this in 3 dimensions, we'll have this hydrogen come out towards you, and then maybe we'll have this hydrogen come in the back, and this hydrogen come in the plane. Again, we're not trying to be exact, and we're not trying to adapt perfection here, but the idea is try to represent something that's 3-dimensional. Right, so 3 bonds and 1 lone pair. So we have our nitrogen. We'll have one of the hydrogens come out, and then maybe we'll have one of the hydrogen substituents go back, and then one of the hydrogen substituents come out in the plane. There's more than one representation of this. We'll have our lone pair sticking out. That sort of bends the molecule. So there's always significant distortion if you have one lone pair. If you have two lone pairs on the central atom, there's even more distortion, as we'll see with the water molecule. So 3 bonds and 1 lone pair. How will I get to 3 bonds and 1 lone pair in terms of my hybridization? Well, as before, I have an s orbital, I have a p orbital, and I have a d orbital. I'm going to take 1 from s, and then I'm going to take 3 from p. See, 3 plus 1 is 4. One of those lone pairs is going to reside in one of those s orbitals. So this too is an sp3 hybridized nitrogen, rehybridized nitrogen. Why is it sp3? Because remember the 3 slots on the p orbital, it's going to take electrons are going to form a bond between the nitrogen and the hydrogen with s and 2 of the p's, and then one of the electrons is going to reside in one of the p orbitals. So this is sp3. 3 plus 1 is 4. 3 plus 1 is 4. It just so happens that one of them is a lone pair. It does not matter. So this is still an sp3 hybridized nitrogen, just like this is an sp3 hybridized carbon. This is an sp2 hybridized carbon because that's how you get to 2 bonds. And so sp3 hybridized carbon, and then this is a polar molecule. Okay, so that electron is going to pull. Okay, it's going to pull upward. It's going to sort of bend the molecule. If we want to compare CH4 and NH3, okay, here's an sp3 with all the substituents attached. Okay, even though it's a carbon central atom. And here is an sp3, same hybridization, with 1 lone pair. So you can definitely see the difference. It's almost like you've taken a hammer and hit the top of the blue nitrogen atom. So that's what the lone pair does. It really distorts this. Okay, it bends the molecule such that the bond angle here is not a perfect 109.5 as you would expect for a nice clean tetrahedron, but the bond angle here is, and I do not know the exact number, but the bond angle here has got to be 107 or 108 degrees, something that's very, very non-optimal. And again, the lone pair makes this a polar molecule. So once again, 3 bonds, 1 lone pair for ammonia, and it's still an sp3 hybridized nitrogen, but that lone pair influences the geometry so that the molecular geometry is now trigonal pyramidal. This is actually like a pyramid. The only thing, it's like a pyramid at the base, but there's no top to it. The lone pair really messes up the geometry. The molecular geometry of this molecule, even though it's still sp3 hybrid carbon, is trigonal pyramidal. The molecular geometry here is tetrahedral, even though it's an sp3 hybridized carbon.